This talk will go over the thin air problem and a solution to it. So the thin air problem is a long-standing problem across all optimized concurrent languages, and a solution should meet the following criteria: that it corresponds tightly with existing optimizations and litmus tests, that it's executable so that the litmus test can be evaluated, and it should integrate cleanly with existing declarative memory models. And our model SMRD solves this. So now we'll cover some background that's needed to understand the thin air problem. We'll be using programs like this throughout the talk. Here, if something starts with R, it's a register, so it doesn't have memory associated with it. And otherwise, it's a global, and it's an atomic memory location. And these are concurrent programs. They're executing together. And we also have diagrammatic representations of these to explore executions of the program. So sequential consistency, this is the intuitive view of concurrency, where we have thread events interleaved in a total order. And the syntactic program order is a subset of this total order. And the thread is connected by these RF arrows, which connect writes to the reads that read from that write. So what are the possible values under SC? We can read before we do any writes. We can perform one write before we do a read, and like this. But we cannot have the outcome of 1-1 because this requires us to perform the writes before the reads, and we get this cycle, so we no longer have a total order. But then here comes along weak memory. This allows this outcome, and it does it by relaxing one of the constraints. This is also why it's sometimes called relaxed memory. And in this case, we can relax the constraint that our total order, that program order is a subset of our total order. So this arrow on the left, we can switch around our ordering, and now we no longer have a cycle, and this is allowed. So the C++ standard has a weak memory model. So what happens if we have an execution like this? Well, we can pluck any value out of thin air. And the reason this is allowed is because cycles in union, program order union RF are allowed. And that's what introduces these values. And the reason this is a problem is because this 42, there isn't really a way to reason about the behaviors that are introduced from this, because there isn't a good reason for 42 being there. And these thin air values can happen even when writes depend upon these. You see these orange arrows because we're taking the values from R1 and R2, but they're supplied also by these. So these shapes should be forbidden. And disallowing these thin air executions while still allowing compiler optimizations is the crux of the issue. And this is what we'll be solving. So one of the ways that compilers optimize is by assuming that undefined behavior never executes. So in this example, we know that division by 0 is undefined behavior. So therefore, both us and the compiler know that not R1 cannot be 0. So the only other value is to say that R1 is 0. So we do this rewrite, and then we can simplify it to a constant. And you see on the left, we have a dependency on R1, and on the right, we have no dependency. So this optimization has removed a dependency here. So putting this in the wider context, we now have T1, which looked like the previous example, And now we have T2 that does some stuff with X and Y. And now we have a shape that looks oddly like our thin arrow example from before here. But we don't have this dependency edge because we're allowed to optimize away the state dependency. And GCC and Clang also think this behavior should be allowed. So that's good for us. And this doesn't look too good, but on line 3, we see that this store of 1 divided by not R1 has been optimized to a move of a constant 1. So it is doing the optimization, so we can observe this behavior. And now we'll go more into the details of the model. So for every write in an execution, we must justify it. So we have this justification structure here that has control dependencies and data dependencies associated with it. And then we have a set of elaborations, which are operations that alter these to produce new justifications. And we also have these program-wide guarantees that aren't part of the justification but sit alongside them, and they capture information about the program. And elaborations can weaken control dependencies with these. So if our program-wide guarantees imply some control predicate, we can remove that because we know this information without having to actually execute. And now we'll go into the example from before, but using the justifications. So we create an initial justification for this write 8, and we leave it as is. This is a true dependency, so we'll just leave that there. And then we create an initial one for 3, and we have a data dependency on R1 here, because the expression 1 over not R1 contains R1. And from here, we can perform a strengthening elaboration. This adds a control dependency. In this case, we'll choose to add R1 equals 0. And this simply means that this write happens in fewer executions. So this is fine to do. And now we have value assignment, which uses information the information about how values are constrained by the control predicate, the control dependencies, to rewrite values in the expression. So here we know that R1 equals 0, and we have R1 here. So we can rewrite that R1 to a 0, and we have now transferred the data dependency of R1 into a control dependency on R1. And this simplifies, like the previous example, into this justification. And now we can perform weakening, which is the operation that we talked about before. With the program-wide guarantees, we know that R1 must be 0 because of the UB freedom. And we can now remove that dependency, and we get this independent write, which justifies the execution that we saw before. So we've removed this dependency. Okay, and now onto our tool. So this tool allows us to explore the executions of the program under our model. You can see here that this structure on the right matches what we saw in the slides. And that this execution is allowed by this. And I started running the tests a second ago, and we see that it's finished. Yeah, the performance of the tool is quite good, and it also handles code with allocations, which former tools could not. Now, in conclusion, we have a solution to the thin air problem, and you can try out the tool by scanning the QR code. That's all.
So we do have time for questions.
Hi, thank you very much for the talk. Yeah, I'm Anton Tkapaev. So a couple questions. This is not the first solution to thin air problem. I mean, to some degree. I heard about some of them. So how it compares with everything else, like from promising, for example?
So this example about UB freedom, in the initial case, the only time where the undefined behavior happens is when R1 is not 0, right? But the only way for that, and it is always 0 if these are ordered. So the only way for it not to be 0 is to do the optimization, which prevents the undefined behavior. Mm-hmm. This is what allows this execution to happen. In promising, what we see is that you can see it, you make the observation that you can do the optimization into a store of a constant 1. So you can you successfully can make that promise. You execute the other thread. You perform the transaction of writing that 1 back in, but then you re-perform this computation. So the rewriting isn't consistent, and then you observe the undefined behavior. So you can have any outcome in this case. So you can introduce a thin air outcome. So in that case, introducing undefined behavior is one way in which promising doesn't quite match up. Does that answer the question?
Yeah, I guess we'll chat a bit more after. Do you have more time? So one other thing I was wondering, so like in the first version of MRD, like I saw a problem that like basically needed to consider all possible values to make a read, for example. Is it still the same here, or you did something about that?
Yes, I think I skipped over like the main contribution to this is that it's symbolic. So the like concrete event structures we had before, where it would split on the reads, like read x1, read x2, up to however many. This is now constrained by symbols, so we don't need to do this concretization. Yeah.
Great, thanks. Yeah, let's chat more.
Yeah.
I was curious about the interaction between sort of out of thin air and undefined behavior. So I think there's this example by Mark Batty that shows that sort of you can have undefined behavior that causes itself by undefinedly spawning another thread that does a load buffering shape. So how do you address this?
So I'm going to answer this twice in 2 different ways. So the first one is if undefined behavior, you can do anything, right? So there's 2 cases. There's one where the code doesn't actually have that thread spawning capability, but because you hit UB, you can now introduce thread spawning. Then there's a case where you can spawn a thread in the code, but you can only access it through doing some UB stuff. In the case where the code doesn't exist, we took an approach to UB freedom, in that the assumptions we make are that it never happens. If you actually reach UB, then all bets are off. In that case, like for example, if this could be 1, let's say it was initialized to 1, then you could actually execute that bit, and any execution is allowed anyway. So in the case that it doesn't exist, we wouldn't have this problem. In the case where it does exist, If you could spawn a thread through actually executing UB, then that is a fine thing to do anyway, because at that point you can do anything, right?
Yeah, so maybe this is best taken offline. I mean, I don't know, you have 200 tests, I have 200 questions.
Okay.
So let's thank the speaker again.